In 1831, Michael Faraday realized that dragging a magnet near a wire creates an electrical current. To control that current, we must look at the math Faraday left behind, these symbols. Let's organize this by isolating our ultimate goal on the left side of the equation. This symbol represents induced voltage, the raw electrical push we are trying to generate. To get a stronger electrical push on this side, we need to carefully assemble the variables on the right side of the equal sign. First, what are we actually pushing with? We need a raw material to create the charge. This is represented by the Greek letter phi, which stands for magnetic flux. It represents the measurable force coming off the magnet. As you can see in this animation, flux represents the specific magnetic field lines that successfully pass through the hollow center of our wire loop. But there is a catch. If you leave that magnet resting perfectly still inside the coil, your voltage output is absolute zero. To generate electricity, the math requires action. We add the Greek letter delta to represent change, and we divide that change by a specific duration of time. By physically spinning the magnet, we force that magnetic flux to constantly alternate. And because we are dividing by time, the speed of that spin dictates the output. Let's test this. Suppose we spin the magnet slowly, taking 2 seconds to complete one rotation. With a baseline flux value of 10, our math looks like this. Now, what happens to our voltage if we apply more force and spin the magnet twice as fast, completing the rotation in just 1 second? Take a moment to deduce the outcome. Here's the mathematical resolution. Dividing by 2 gives us an output of 5. Dividing by our faster time of 1 gives us a 10. The math proves a highly practical rule. Minimizing the time variable by spinning a magnet faster results in a massive increase in electrical output. This photograph shows an early industrial machine hall. Engineers built these heavy iron machines for one reason: to force large magnets to rotate continuously. But the underlying equation remains strictly identical. Whether we use millions of gallons of falling water, pressurized steam, or massive wind blades, modern infrastructure is just a physical tool built to violently spin turbines and make that time variable as small as possible. Here's your final summary cheat sheet. Go ahead and screenshot this frame for reference. You have the electrical push on the left, created by a changing magnetic field on the right, accelerated by time. Distilling the physical world into these 3 variables allowed us to build the modern electrical grid. Faraday's 1831 discovery remains the mathematical blueprint for the mechanical generators we still rely on today.